Hello, students. Had a couple questions here before the exam, so I'll post those. Some of them were about relations and functions. So here in the where am I at? The chapter review. I just grabbed these because here's a couple. So these are kind of verbal descriptions of a relationship from one set to another set. If a correspondence is a function, find the range. But again, you're looking to see if it is a function first and foremost. So if you say this is the set of books and B is a set of natural numbers, to each book corresponds the number of pages in the book. So when you think about that, it is definitely possible for a lot of books to have the same number of pages. That's possible, but that isn't the definition of a function. A function is that relationship where each element in the first set maps to exactly one. So what you want to do is you want to think about, well, what would it look like? What would it look like then? So if you picture that. So then whatever book you pick in the first set, okay, so here, there's some kind of book over here, right? And here's the number of pages. Okay. So if you take a book, whatever that book is it possible for that book to go to, 700 and 529? Is it possible for the same book to map over here? And you'd say, no, that's not possible. It either the book has 700 pages or it has 529 pages. It's not going to be a both situation. So this can't happen. And every book that is in a library has to have some number of pages. So it doesn't make sense for their, maybe this book has 529, maybe this book has 529 as well. That's totally fine. And then it wouldn't make sense for this book to not be mapped anywhere, which would mean it's a book with no pages. And that would be not something that would be in a library. So I would definitely say this one right here meets the definition of a function. And then find the range. Yeah, I have no idea how big the biggest book is, so I would just say that it maps over the range. When it says find the range, this isn't one where you would be finding the actual values. You just say it is the set of the page numbers for all the books in the library. That's how you could describe it. When they come down here, sometimes with some of these other problems, you can actually find the exact range. Um, so here, if x is even, then you get an output of 0. If x is odd, then you get an output of 1. So the range would just be the numbers 0 and 1. That would be the range. You could actually find it's only those. But for the problem with the books in the library, I mean, you have no idea, right? Because you wouldn't want to say all natural numbers, because then I don't know if there is a book that has 699 pages. I don't know that. So definitely that would be the codomain, but wouldn't be the range. Okay. All right, let's talk a little bit more. What else could we do? Doop, 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 doop. Let's go whiteboard. And here we go to the whiteboard. Zoom has two whiteboards now, some kind of collaborative whiteboard space, which is pretty cool. If we were doing like a Zoom class, then you'd all be able to kind of share the board and kind of jot down things and show what you were thinking. But for what I'm doing here, I'll just use the traditional. Okay, so we've been thinking of like a function goes from one set to another set, but honestly, there's nothing wrong with that set kind of mapping back to itself. That would be like the real numbers mapping to the real numbers. That happens all the time. So don't think it has to be a different set. It just has to map from one set to another set. Those two sets could be equal. So this might be my function f. So again, over here, I could have, let's just say an A, a B, and a C, all right? And over here, then I would have an A, a B, and a C. Okay, so if you're looking at kind of what reflexive would look like in this situation, you would say, okay, well, C has to go to C. Oops, I don't want to use the same color. I want to use a different one for the map. There we go. C has to go to C, B has to go to B, and A has to go to A. So this is kind of what it would look like for reflexive. Okay, so now look at this. Is this a function? And you'd say, well, yeah, every input value maps somewhere, so it has to go somewhere, and each one goes to exactly one place, right? But then if If you also had A goes to B, now right away it'd be like, oh, now maybe we're talking about symmetry or transitive. So A goes to B. Now you go back to the start. Where does B go? B, I don't know. If it is symmetric, then B has to go up to A. It has to. So you can visualize it this way. It's not doesn't tend to be the way that I was drawing them in class. So how I did it in class is, let me just try and draw a line here. I would just do it on one picture. So here's A, here's B, and here's C, or whatever numbers you might have, right? So then if it was reflexive, then each element has to map to itself. So it would look something like this. Okay. But just understand, like that arrow that goes to itself is the same thing as saying start at C and then end at C and drawing this kind of arrow right here. Okay, that's the same because C went to C, and because these sets are identical. So then if you did have A goes to B, if A goes to B, we'd kind of draw it like this. And then if B goes to A, we draw it like that. Again, that's drawn all on the same piece. But I could ask you the same question. Is this one over here, is this a function? And you'd have to say, well, let me see here. Does every point go somewhere? Yes. And does if it goes from one point, it can go to exactly one point. And that's not going to work here. And your justification could be, well, B goes to B and also B goes to A. So right there, you could just say, hey, that fails. That's not a function. Okay. All right. So anyway, that's the idea here. Let me jump back to the other screen here. Okay, so when we were back doing relations, where was that? 463? Was that about where it was? We're close. 453. Let's go 451-ish. Okay, so here we go. Those are the connections. So let's go to relations then. No, that's all the algebraic pieces. Maybe it was more in the function section. Let me take a look there. There's that. Okay, here we go. Oh, I did. Here we go. So when you're dealing with functions, we saw we could look them many, many, many different ways. Here we go. So arrow diagrams. Let's see here. Let me go back. I'm going to go back to the beginning in 4A just because I think there's some here. Yeah, here's some. Again, this is make an arrow diagram for each of the following. And it says when doubled is. Okay. Now this is great because they're using two different sets, A and B. But again, you could have used just like from A or from B to B. You could have said the same thing. So let me show what that looks like. Okay. So if I say the rule is when doubled is. So the way that looks is if you start with the number one, and then you'd finish the sentence with whatever's in there. One when doubled is 2. Okay. When doubled is 2. Okay, so what would that represent in the picture? That would be from 1, I'd have an arrow going to 2. Okay, because 1, when I double it, is 2. All right, so that's the rule. Down here we have is greater than, fine. 1 is greater than, well, it's greater than none of those. 2 is greater than 1. 3 is greater than 2, but 3 is also greater than 1. So again, you can kind of picture kind of how that operation is working. That's is greater than. You can do is less than. I think in class we did is less than and less than or equal to, I believe, when we were exploring these. Okay, but let's see here. Let's go back up here. So what I wanted to say is this: you're in charge of drawing it. You can draw it from the same set to the same set. But yeah, when doubled is. So if I just did B, that's probably what I would have done. Here's B, and I would just say, look, I'm mapping over to B again, which is like saying, hey, take the natural numbers and map to the natural numbers. Okay, but let's just say we're taking a subset of it. So 1, 2, 3, 4, 5, 6, 7. That's fine. I'll go 8. I guess I'll put 8 in there too. Okay. And then over on the other side, I'd have 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay. So now I'm mapping it to itself, which means, and this is where it kind of gets a little strange, I could have just said, why don't you just keep all the points in there, Scott, and just draw the arrows to themselves when it's needed. So as an example, your arrow diagram could absolutely look like this. When doubled is, okay, well, 1 when I double it is 2. Perfect. 2 when I double it is 4, right? 3 when I double it is 6, right? 4 when I double it is 8. 5 when I double it in this situation is not in the set. But if you did have all the real numbers, you could say, well, 5 has to go to 10, 6 has to go to da, 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 right? And so then you can kind of look at this relationship that's right here. Is it reflexive? Is it symmetric? Is it transitive? Let's take a look. So is it reflexive? Well, let's see here. 1 would have to go to 1, but 1 when doubled is 1. That's not true. So there's my counterexample. Symmetric. 1 goes to 2, right? 1 goes to 2, so 2 has to go to 1. No, because then you'd say 2 when doubled is 1. That's not true. So there's my counterexample for symmetric. Is it transitive? Transitive. Let's see here. So 1 goes to 2, right? 1 goes to 2, and we know 2 goes to 4. So I'm supposed to have 1 goes to 4, but it would be wrong to say 1 when you double it is 4. So that isn't going to happen. That's why transitivity is false. So it's not reflexive, not symmetric, not transitive. Is it a function? Well, each point has to go somewhere. And for every number you can think of, when you double it, you do get an output. And each one, when you double it, gets exactly 1 output. So if this was all natural numbers, then 5 does go to 10, and 6 goes to 12, and 7 goes to 14, and 8 goes to 16. Every number has a double in that set. So would it be a function if we were saying is double when doubled is? Yeah. Yeah, that meets the definition of a function. Okay. So I think that covers everything. At least I think so. Let's see here. Let me stop sharing for a moment, make sure. Function. Yeah. So anyway, there you go. There's those pieces. So yeah. And again, looking at it again, if it's just you can have it as 2 separate graphs and seeing it going, but I just wanted you to show what we were doing in class. You could have absolutely taken that and built 2 of them to see the arrows going. It doesn't matter which type it is. It's just if it starts at A, it can go exactly one place. That's it. So if A goes to A, that's it. A cannot go to B if you want it to be a function. All right. Hope that helps. Off you go.